Okay, on to section 6.3, the equidistance theorem. All right, traditionally this is one of the more difficult sections that we do in geometry, so you definitely want to, if you're asleep right now, you definitely want to wake up. Okay, so we're going to start out with a proof, and what we're basically going to do in this proof is we are going to prove what is known as the equidistance theorem. So in this theorem, or in this proof here, it's given that this is congruent to this and that this is congruent to this. And what we're trying to prove is that PB is the perpendicular bisector of ER. Okay, so what we need to do here is we need to prove that this is a right angle, so it's perpendicular, and we need to prove that this is congruent to this. Now, you know, it would be nice if we could prove that either the upper triangles or the lower triangles, so for example, if we knew that these upper triangles were congruent to each other, we could do this. Or if we could prove that these two bottom triangles are congruent to each other. But the information that we give you doesn't allow you to do that. So we have a proof, detour proof here. You need to prove, because you got reflexive all the way down the middle, you need to prove that the big triangles, okay, from these triangles, are congruent to each other first, and then you can use information from those big triangles to prove that some of the little triangles are congruent. Okay, so let's write this out. Kind of gave you some information here to give you a head start. It looks like you're trying to prove that the big ones are congruent, so PB is congruent to itself. It's just reflexive property. So the triangles are congruent by SSS. And of course, you got 1, 2, 3 from that. Okay, step 5 here, looks like I'm headed towards proving that I believe the upper triangles are congruent. So I'm going to need these two to be congruent to each other. So I'm going to use these angles, angle EPS congruent to angle RPS by CPCTC, and I'm going to use those angles to prove that the upper yellow triangles are congruent to each other by SAS. So I still need a reflexive here. I know that PS is congruent to itself. And now I can say that those triangles, triangle EPS is congruent to triangle RPS by SAS. Okay, so that would be by steps 1, 5, 6. And now, because of that, I can say that, because I'm trying to say that PB bisects ER, I can say that ES is congruent to SR. Right here, ES is congruent to SR. CPCTC. And then, so if two congruent segments, you have a segment bisector. And now, as I had mentioned earlier, you can say that these two angles right there and right here are congruent to each other. And we're headed towards using that. So CPCTC, you know that those angles are sup to each other. PSE sup to angle PSR. If you have a straight angle, then they're sup. And now I can do RAT, because, okay, PSE and angle PSR are right angles by RAT. And that, of course, comes from knowing that the angles are congruent and supplementary to each other. Now I can say that they're perpendicular. Because if you have right angle, then you have perpendicular segments. And now, because of what I showed in step 13 and what I showed in step 9, these two together, I can say it's the perpendicular bisector. Okay, so what have we just proven here? Let's write this out. Okay, so definition of equidistant, equidistance, same distance. Okay, so if I have a point here, this point, and this point, are going to be the same distance from each other. So A is the same distance from B as it is from C. That's equidistance. The key theorem, the important theorem, the critical theorem, the primary theorem, okay, is stated as such. If 2 points are equidistant, there's that word that we just defined, from endpoints of a segment, then those 2 points determine the perpendicular bisector of that segment. So, the theorem is kind of a long one, okay? It's a mouthful. If 2 points are equidistant from the endpoints of a segment, then those 2 points determine the perpendicular bisector of that segment. And you do need to write it out. So you're going to whine. I see you rolling your eyes at home already. Again, if 2 points are equidistant from the endpoints of a segment, then those 2 points determine the perpendicular bisector of that segment. However, the nice thing is this. Okay, if I look at this proof up here, and this proof was a 14th step proof. Okay, so remember, it was given that this is congruent to this, and this is congruent to this. So that means that here's 1 point that's the same distance from the endpoints of this segment. Okay, so point P is 1 point that's the same distance, equidistant, okay? Equidistant from the endpoints of ER. Point B is a second point, so there's 2 points that are equidistant from the endpoints of ER. If you have 2 points, here's 1, here's 2, that are equidistant from the endpoints of the yellow segment, then those 2 points, P and B, determine the perpendicular bisector of segment ER. So, if I were rewriting this proof over here to the left, my first step would be the givens, PE congruent to PR, EB congruent to RB. That would be given. And my second step would be that PB is the perpendicular bisector of ER. And the reason would be what we said down below. If 2 points are equidistant from the endpoints endpoints of a segment, and those 2 points determine the perpendicular bisector of that segment. 2 points are equidistant from the endpoints of a segment, and they determine perpendicular bisector of that segment. Okay, so you basically have here a two-step proof for what used to be a 14-step proof. It is a serious shortcut. Okay, so the nice thing is in this section, the proofs are all very short. There is a corollary to that theorem, and I'm just going to call it the reverse theorem. Basically, it is if a point is on the perpendicular bisector, then that point is equidistant from the endpoints of the segment. Okay, so basically, if I go back up to the diagram, the original diagram, if I pick another point on the perpendicular bisector, let's pick this point right here, then I know that this is congruent to this. And if I pick a point here, that is congruent to that. And if I pick a point here, that is congruent to that, and so on and so forth. And that's all that theorem says. Let's flip over to the backside and we'll try a few proofs just to get a sense of how you would use this. All right. All right, we're on the backside here. Let's try a few proofs. If you notice, all the diagrams are going to look sort of like kites or folded up kites, because if I draw on the radii here, it looks like a kite that got folded up. Or down at the bottom here, there's another, I draw these in, it looks like a kite. And then if I look at this one down here, this is a kite that got folded up. Okay, so I got a bunch of diagrams here, and that's the main thing about figuring out when you need to use the equidistance theorem. It's when you see a diagram that looks a lot like a kite or a folded up kite. Now, when you're trying to prove that something is a perpendicular bisector, you will use the equidistance theorem. When you are given a perpendicular bisector, like down here in problem number 3, that's when you will use the reverse. So, for problem number 1 here, keep in mind that all these proofs are going to be very short. So problem number 1, it's given that angle 1 is congruent to angle 2, angle 3 is congruent to angle 4. Hopefully you can see that using if angles and sides, this is congruent to this, and this is congruent to this. So, Tn is congruent to Th, and S is congruent to SH. If angles, then sides. There's a lot of that, by the way, in this section. A lot of if angles, then sides, if sides, then angles. Now, if I have that, you can see, hopefully, that I highlight the segment. You can see that there's 2 points, 1 point, 2 points, that are equidistant from the endpoints, here's the endpoints, of the yellow segment. Because those 2 points are the same distance from the endpoints of the yellow segment, those 2 points determine the perpendicular bisector of the yellow segment. So then that means that TW is the perpendicular bisector of NH. And that would be if 2 points are equidistant, okay, the rest of it out. So if 2 points are equidistant from the endpoints of a segment, then those 2 points determine the perpendicular bisector of that segment. Okay, next proof. I have circle C, so I know that I have radii that are congruent to each other. And it's given that EI is congruent to EL. So just from looking at that, you focus on this segment right there. Hopefully you can see there's 2 points. This point is equidistant from the endpoints of the yellow segment. It's the same distance from the endpoints. And this point is the same distance from the endpoints of that segment. So therefore, these 2 points determine the perpendicular bisector of the yellow segment. Okay, so that, and then you can say that, well, it's a perpendicular bisector, so that means that Ri must be equal to congruent to RL. So let's write this out. Circle C, that's given. Draw in the radii, so draw in CI and CL. 2 points determine a line. Step 3, I know that CI is congruent to CL. These radii are congruent. Step 4, I know that EI is congruent to EL, that's just given. And so now I have 1 point and 2 points that are equidistant from the endpoints of the segment, so that means that ER is a perpendicular bisector of IL. Okay, and I'm just going to cheat here. I need you to write it out, don't forget. It's the equidistance theorem. 2 points determine the perpendicular bisector. If 2 points are equidistant from the endpoints of a segment, then those 2 points determine the perpendicular bisector of that segment. And now I can say that Ri is congruent to RL. Now, I can say that it's because if a segment bisector, then congruent segments. Or what I could have said here is I could have also used the reverse, which basically says that if a point is on the perpendicular bisector, the perpendicular bisector is the blue line, then that point is the same distance from the endpoints of that segment. All right, one more proof here. AE is a perpendicular bisector of both of these. Okay, so it's a perpendicular bisector of this one, and it's the perpendicular bisector of this one. So if AE is the perpendicular bisector, then that means that this point is equidistant from the endpoints of the segment, and because it's also on the one that bisects the orange line, I also know that that's also equidistant. So it's congruent because A is equidistant from the endpoints of C and G. So the way I'm going to write this is step 1 is there. Step 2, I know that AB is congruent to AF because A is equidistant from the endpoints of B and F, endpoints B and F, and AC is congruent to AG because A is equidistant from the endpoints C and G. That is just the reverse, and again, you need to write it out. Right out. Okay, because I know this, then BC is congruent to FG, and that's just going to be a subtraction. Okay, and notice again, these are short proofs. Most of the proofs in this section are 5 steps or less. Generally, they are not long proofs at all, because this is a shortcut. So make sure you learn it. Make sure otherwise you will be writing out 14-step proofs instead of writing out 2-step proofs. Okay, I'll let you go ahead and give it a try.